Okay, so I just want to take some time to run through some of the basics of the video that we'd have on the airframes. This would be the kind of a short version of the lesson that we would be normally having for you in class. So the first thing I want to talk about is the types of airframe construction. These are the same terms and the same words that you'd hear in fixed wing. So we're talking about steel tube construction, monocoque construction, semi-monocoque, and composite. And you'll see all different examples of these on aircraft, on helicopters. So the first one is tubular construction. Tubular construction used to be really common. You still see it quite a bit. It's steel tube frames, typically 4130 chromoly steel, and the tubes are welded together to create the truss. Sorry. Um, steel tube frames. They're very high strength for their weight. That's why they were so popular. So you can get a lot of strength in their weight. It is possible to repair some of them, but if you do repair them, you need a jig. Now, some manufacturers like Robinson, they pre-stress their frames, so those ones you can't repair, but other manufacturers with a steel tube frame, you can repair it, but it's got to go back and be repaired in a jig. It's not just something you can do in the field. The downside, and the reason you don't see a lot of steel tube structures anymore, is they are very expensive and difficult to manufacture. A lot of them have to be built by hand, which is why they used to be popular when manufacturers built stuff that way. But now you see that less, and so now these frames are kind of going out of favor. Like I said, some of them still exist, but they're not as popular as they used to be. The next style is monocoque. Now, monocoque, the reason I've got a picture of an egg there is because monocoque is a stressed skin. So just like you'd have on an egg, the all the load, all the strength of the structure comes from the skin of the structure. So there's no underlying support. You've probably had that science class where teacher pushes on an egg this way and it's got lots of strength on it. You can actually put quite a bit of weight across an egg, but if you try to put the weight this way across it, of course, you end up with an omelet. So steel structures that are made out of monocoque construction, they're lightweight, very very useful. Being that monocoque structure, being lightweight, it allows the manufacturer to save on a lot of internal pieces, a lot of internal extra parts, so it keeps the part count down. The bad side to this is they are fragile. If you've got dents or anything like that in them, then that structure is going to have to be possibly replaced. You may not, you have very limited damage tolerance. You may have to replace the part. You may not be able to, you may not be able to use that part further. So the next common replacement for that is semi-monocoque structures. Now, like a monocoque, there's still a certain amount of load being taken by the skin. However, a lot of the structure underneath is reinforcing that and supporting that. So what this means, it's lightweight, but it's heavier than monocoque, but it's cheaper to manufacture, and you can repair it in the field. So, like you guys have probably done that in your structures class already. You guys know how to do repairs for these. So that's why semi-monocoque is so common. You can do the repairs, you can do the work in the field, and it's still kind of a mixture. So there's a view of the same structure as the first picture, but from the inside, and you can see the different trusses and formers inside the structure underneath it. Next one is composite. Now, composite structures, that's a broad term. So typically you'll hear about carbon fiber and fiberglass listed as composite, but also like I've got in the picture here where we talk about aluminum honeycomb. So that's referring to this structure inside here. So you'll have skins on the outside. These could be aluminum, they could be fiberglass, and then there's a honeycomb structure underneath here to take the shape as well as to help create the strength. Composites are showing up everywhere. You're seeing them in all the aircraft now because they are lightweight. They are joys of this. You my phone buzzing in the background. They're lightweight. They work. You can do a certain amount of repairs to them in the field. And you can also design shapes to whatever you want them to be. It's not necessarily going to be what you're limited to by simple construction techniques. If you can dream up a shape, if you can design something with composite materials, you can build that shape. So on a helicopter, on an airplane, it's typical to have one style of construction for the entire airframe, but on a helicopter, that's not always the case. Because you remember earlier on when we talked about the tail booms, these tail booms are bolted on to the aircraft, so that means the construction of those can be one thing versus the forward and the intermediate airframes. So on here, we'd actually see three different construction types. The tail booms, quite often, are going to be a monocoque construction, lightweight, strong, but fragile, so you don't want to dent them or anything like that. Okay, so quite often if you have a dent on there, the part's going to have to be replaced. In the center section here on the Bell 206, this is a semi-monocoque construction, and the forward construction up here is actually a fiberglass. It is a composite structure with an aluminum honeycomb. So you get all the different styles in one sort of airframe. There's just some pictures from the notes that you would see examples. So there's the tail section of KGO, and this was another airframe looking at exactly the same piece. You can see with the skins removed, you can see the structure underneath it. So the tail booms, talked a little bit about the tail booms already. Purposes of the tail boom, obviously the big reason we have a tail boom out there is to get that tail rotor gearbox out there so we can get the tail rotor out there. So the tail boom, it's got to be light, it's got to be strong, it's got to support the vertical and the horizontal stabilizers, it's got to support the drive shaft, but we want to do it with a minimum amount of weight involved. Now, one of the things that happens when a helicopter flies forward is it has the tendency to dip nose down. So as the helicopter accelerates, we point the nose down. Now, obviously, if the nose tips down too far in flight, that's going to be uncomfortable for the passengers and uncomfortable for everybody in the aircraft. And ultimately, it's going to increase the drag, so it's going to decrease the efficiency of the aircraft. So manufacturers do a couple of things to limit that. The first one is the horizontal stabilizer. And you'll notice sometimes people pick out that the stabilizer is actually an upside down wing, and that's exactly what it is. So a horizontal stabilizer is actually producing a lift force, but it's producing lift that direction. So that means it's actually pushing the tail of the aircraft down instead of trying to lift the aircraft. If you look at all the horizontal stabilizers in the aircraft we have in the hangar, they're all going to have that same reaction. They're pushing the tail of the aircraft down. So, and because it's an aerodynamic force, it only works as the aircraft increases in speed. As the aircraft accelerates, then it's going to push the tail further down. The other thing that the manufacturers do is they mount the mast not at 90 degrees to the airframe. And so in this example here, you can see that the mast is at a 5-degree forward tilt, and that's what these angles here are trying to show you. That means when the airframe is sitting level, so ideally level in flight, then the aircraft will have the rotor system already biased forward, so that way in forward flight, the airframe can sit more level and the mast is going to sit forward. Now, one of the things this means, though, is when the aircraft comes into a hover, the tail is actually going to sit low. So the aircraft will sit tail low in a hover, but in forward flight, it might sit more level. That's going to be more comfortable for the passengers and for the people on board the aircraft. Some other things that we mount in the aircraft to stabilize or to counteract for torque is going to be vertical stabilizers, winglets, and strakes. Vertical stabilizers, a couple of different pictures here. I'm actually going to go to the one. It's a little clearer to see. So this is the EC120. When you look at the EC120, you can actually see the shape of the airfoil. Okay, so you notice that the back of this isn't a straight line. You can see how it's cambered off to the side. So this is an airfoil that, as we're in flight, it's going to produce a thrust force, and that thrust force, again, aerodynamic, it's going to help offload the tail rotor. So what the vertical stabilizer does is, as the aircraft accelerates, the vertical stabilizer creates more lift, or in this case thrust, and that helps keep the aircraft flying straight as the aircraft speeds up. That means that the pilot can use less tail rotor authority in forward flight, So this kind of counteracts. That's why if they have an emergency with the tail rotor, they'll do a, as long as they keep the aircraft moving forward, they still have that, removes the tendency for the aircraft to spin. Having the vertical stabilizer canted like that is also going to mean that they need less power from the tail rotor to keep the aircraft from spinning. So it's quite useful that way. Now, sometimes in certain types of aircraft, the vertical stabilizer doesn't provide enough of a correction. The vertical stabilizer here can only be so big. Eventually you're going to run into issues with the ground. If it gets too tall, the structure becomes too big. So what some manufacturers will do is they will add these winglets onto the horizontal stabilizers. The winglets on the horizontal stabilizers are going to do a couple of things. They're going to increase the efficiency of the horizontal stabilizers, but the winglets are also going to have that same effect like the vertical stabilizer does to help keep the aircraft pointed straight and relieve the load that we need to apply to the tail rotor. The next is the strake. Now, strakes are a bit of an unusual thing, and they kind of almost come into that category of why didn't somebody think of this sooner? Now, on this picture, the strake is actually these yellow pieces along here. And these strakes, all they are is they're just, just bent pieces of aluminum. If you were to look at them really closely, you would just see that they're just a L bracket like this riveted to the side of the airframe. And what they do is they affect the airflow from the main rotor going over the tail. So what some smart person figured out is that the air coming off of the main rotor, so let me try this here. So the air coming off of the main rotor, there we go, this way. That didn't work out very well. So anyways, the air coming off of the main rotor is basically reacting around the tail boom. And in this example here, without the strake, these different colors represent the airspeed. And you notice that the airspeed on both sides of the tail boom is the same. What the strake does right here is disrupts the airflow going down this side of the tail boom. What that means is it changes the speed of the air here relative to the speed on the other side. So on this side, we have moving air. On this side, we have faster air. As velocity increases, pressure decreases. So we still have, relative to the two sides, that because the velocity on this side is faster, it's going to have a lower pressure. Because it has that lower pressure airflow on there, that means that the airflow on that side of the tail is going to cause the tail to go in that direction. Hold on, I got to change that pen. That really sucks. There we go. So the tail boom is going to go in that direction. Basically, what it does is it's turning the tail into a wing. So that means the downwash from the rotor system is actually helping to compensate for the torque. Now, this doesn't totally replace the tail rotor, but it does help alleviate some of the load and some of the stress being applied by the tail rotor. In the course, you will see I've put a link to the BLR fast fin. I've put the link directly in the course homepage, so if you look at that link, it's got a pretty good graphic. It's a little bit of a sales pitch, but bear with it. It's got a good way of explaining it. Now, on some helicopters, you will see what they call synchronized elevators. So the horizontal stabilizers that I've been talking about so far are fixed. They do not move. They're bolted into one position, and that's it. They stay put. A synchronized elevator is a horizontal stabilizer, but it has the ability to move. So as the pilot makes a cyclic control input, the stabilizer is actually going to change position. And so what I have is these two pictures here. So this is a Black Hawk. So you can see this aircraft here in forward flight, and you can see that the horizontal stabilizer is relatively level with the airframe. However, same aircraft type, don't mind the change in the paint job, different position. Now you can tell we can safely assume by these two guys hanging straight underneath the aircraft here that this helicopter is in a hover. And so that means the cyclic position is going to be quite a bit different, and you can see how the horizontal stabilizer, synchronized elevator, is in quite a bit different position. This is going to help accommodate for a wide range of CFGs, and it's also going to help increase or decrease the efficiency of the horizontal stabilizer based on the flight condition. It's never perfect, but it does help, and it does help create some offset. I want to talk briefly about windshields. We've talked a little bit about windshields in the hangar. Just want to explain a couple things. Windshields on helicopters are often a structural component. They can be holding that front half of the airframe together, so they can be pretty important. Something to consider when you are installing these. Remember when we looked up the torques, we noticed that the torques on some of these fasteners was quite light. This nose section here is of an A-star, and this picture doesn't do it justice. This window is not flat across here. It's actually got a very significant curve across the front of the aircraft. And so what would happen when you get that window, it actually comes, well, it looks like something from IKEA. It comes flat packed. And when you bolt that window on, it has to be shaped around the airframe. So you start with all these fasteners down the middle here, and then you work out in a cross pattern going across the windshield. If you mess up this installation procedure and you mess up the torques, these windows crack, and then you're sending this window back to the manufacturer or replacing it with a new one just because of an installation error. So you've got to be really careful when you're installing these things that they go in the right way. Other styles of windows are rubber mounted, so you'll see rubber mounts putting the windows in. You won't see that necessarily for windshields, but you will see that for side windows. And you've already heard me swearing in the class, don't touch the windows, they scratch really easily. Here's some examples of damage limits for the windows. This is from the Robinsons. And so you can see here they talk about crazing around the mounting holes, and they also talk about limitations for cracks. And they're like, oh, look, you can have a crack here as long as you stop drill it. But read the fine print. It's got to be less than 1/4 of an inch. So they're not talking about a lot of damage. It's got to be really restrictive. So they don't want to compromise the integrity of those windshields on there. Just for entertainment value, we've got a couple of photos here. For anybody who's thought about how much wind damage a windshield can take, there's a couple of pictures here. There's a close-up of it right here. This was an R-44 that had an unfortunate situation with a bird. Fortunately for the people inside the aircraft, on this side here, this was a news gathering aircraft, and it had a camera and such like that here, or a monitor, sorry. The monitor took the brunt of the impact, and none of the people inside were hurt. A little bit frightened, and unfortunately the bird had a pretty bad day. So these windows are not impact proof. There are some manufacturers now that are going to impact resistant windows. They would be able to take a small bird, maybe that kind of thing. They're certainly not going to pass the frozen chicken test. But the penalty to that is a weight increase. So a lot of operators are choosing not to option these windows because the weight increase has a negative effect on their useful load. So most of the aircraft that you're going to be around, they're just going to have the regular plastic windows on them. So you got to be really careful with those. The last couple of slides in the presentation are about lifting and jacking the aircraft. Now we've already done the labs about those, so I'm not really going to rate too much on those, but just be aware that the slide's there. So hopefully this has helped. If you've got any questions, send me a message and we'll take it from there. Thanks.